Now that we know what functions are, we can start to look at this concept of an inverse function. So on the Cartesian plane, there are some well-known lines, and one of them is this line here, y equals x. And an inverse function is essentially the reflection of a function, whatever's happening on this side, it's a reflection in this line over to this side of the line y equals x. So we can maybe just start by looking at one point. So let's look at a point here. This point would be the point -1, -2, -3, and then +2. Remember, we always list our x-coordinate first. If I were to reflect this about the line y equals x, we would note the following. The coordinates would switch around. So -3, that was the x-coordinate for point A, becomes the y-coordinate for the reflection. And 2, which was the y-coordinate for A, becomes the x-coordinate for the reflection. So when we work with inverses, what we're going to do is we're going to take our x and y coordinates and we're going to map them in such a way that y and x swap places. Okay, that's the foundation. Let's put this foundation to the test with some functions. So here we've got two functions, and you'll see they'll both pass the vertical line test. So they are definitely functions, like we saw in the video before this one. But now let's have a look at how we would get the inverse of this function. So what we saw was that the inverse means that your x and your y coordinates are going to map, and they're going to reflect in such a way that they switch around, and we look at y and x. So let's apply that here to this straight line graph, y equals 2x plus 2. This coordinate here is 1 and 1, 2, 3, 4. So when I plot the reflection of that, I'm going to plot the point 4, 1, 2, 3, 4, and 1. That's going to end up there. Then I'm going to take another one. Let's take that intercept there. That's going to be the point 0 and 2. So when we reflect that, we're going to plot 2 and 0. That'll be there. 2 and 0. Then let's take one more point. Let's take this one here. On the line y equals x, what do we notice? -2, -2. That makes sense, seeing as though the equation actually tells us, let's write that equation in, y equals x. So y does equal x when they're both -2. And so even when we swap them around, we're going to actually end up with the coordinates there, -2 and -2. Okay, and then we can join these coordinates and we will form the inverse function. So there we have it. And then just a note on the notation, if we were dealing with, let's call this red one the function f, then our inverse function would be f to the -1. Okay, and it's a function of x, they both are. So there we have our function, our original function, and then the inverse function, which reflects beautifully about the line y equals x. Okay, we can do the same thing here. We're given the graph y equals x squared. Let's take a couple of points. This origin point here is going to still be, because 0, 0, you can swap that around, you're going to end up with exactly the same coordinates. Okay, let's take this point here. This is currently the point 1 and 1. Oh, and once again, when we switch that around, we're going to see that is also a point on our reflection. Okay, let's take something up here. Let's try and see, what are we looking at? 1, 2 as our x-coordinate, and 1, 2, 3, 4 as our y-coordinate. So the point 2 and 4, finally we're going to have one that actually swaps in a way that is interesting. 1, 2, 3, 4, and then 2. So 4 and 2. Okay, and now let's have a look at some points on the other side. What are we dealing with here? Here's a point. This is the point -1 and 1. So I can definitely switch that one around. It's going to become 1 and -1. So that's going to be down here, 1 and -1. And then let's take that biggest point there too. That is the point -2 and 4. Okay, and we're going to switch it around and we're going to say that's 4 and -2. And then we can join these. And what you'll see is that we have formed the parabola on its side. It's a reflection about the line y equals x. Now what you've hopefully noticed is that this reflection, this inverse, is not a function. Can you see that? Because it's not passing the vertical line test, we are cutting the ruler here and here, and that is a problem. So we formed an inverse, but we've actually formed an inverse relation. And if we want this to be a function, we are going to have to restrict the domain. And that's something we're going to look at a little bit later on. But for now, let's pay attention to how we actually determine the inverse, the equation of an inverse. Because what we can do now is we can take some points on this line and we can determine the equation of this line. So y equals mx plus c, and we can solve. And what you'll notice is that based on the fact that x and y switch around, there is also an algebraic way to do that. And so that's what we're going to look at next. So in an example like this, where we are asked to determine the inverse of a function, what we can do is we can remember the fact that x and y maps to y x. Okay, so that is what a reflection about the line y equals x would look like. And so what I need to do in order to answer this question is to understand that f of x would be representing the y's equals 2x plus 4, and then to say, well, I'm going to apply this, and I'm going to say, instead of y, I'm going to say x is equal to 2 and then y plus 4. So what I've done is I have applied this logic about reflecting in the line y equals x to my algebraic equation. Okay, and once we are here, we are going to want to put this in the standard form. So let's move the 2y over. So we'll be sitting with minus 2y equals, we're going to move that x over 2, it's going to become minus x plus 4. And now, if we want to have y on its own, we're going to need to divide every term by minus 2. So we'll then be left with an equation y equals minus x over minus 2, so that's just a half x, because the minus and the minus cancel. A plus and a minus, there is a minus. 4 divided by 2 is 2. So the equation of the inverse is this thing here. Y is equal to a half x minus 2. Now, if we were to sketch these functions, they would look something like this. So we've got the function f of x, and we've got its inverse here, f to the minus 1 of x. And you'll notice, just based on these equations, you can quickly work out the x and the y intercept here, and the x and the y intercept here. But what you'll see is that these switch around. So 0 and 4 becomes 4 and 0. A point like this, minus 2 and 0 becomes 0 and minus 2. So there we've taken an algebraic way to find the reflection here in the line y equals x, and that is known officially as the inverse function. Okay, let's apply the same principle here. So f of x equals a half x plus 3. So again, what we want to do is we want to swap around, and we want to say instead of y, we're going to call this x, and then instead of x, we're going to call that y. So we've switched out our x and our y's based on what we know about inverse functions. Okay, then we're going to move that half y across, so we're going to have minus a half y, because we want the standard form, is equal to minus x plus 3. And then we need to divide everything by minus a half. Okay, be careful here, that's the same as multiplying by negative 2. Okay, so be careful when you divide by fractions, don't confuse yourself. You want to be clear on your answers there. If you need to, use the calculator. Okay, so minus 1x divided by minus a half x, that's going to give us positive 2x. And then positive 3 divided by minus a half is going to give us minus 6. So there we have our new equation. And if you were to draw the two, you would once again see that f of x and f minus 1 of x are mirror images of each other in that line y equals x. Okay, and fortunately, since everything here is a straight line and everything here is a straight line, these are going to be functions. Let's look at some quadratic ones, because this is when it gets very interesting. So they've asked us here to determine the inverse, and then to restrict the domain on the original function so that the inverse is a function. Okay, what is a function? A function needs to pass that vertical line test. Okay, so let's just have a look at what we're doing, and then we can make some decisions about restricting the domain. Okay, so the first thing we want to do is we want to say, all right, in the place of y, we're going to write x, and in the place of x, we're going to write y. And then we're going to do everything we can to get y on its own so that this is in the standard form. So divide by 2, we'll end up with y squared equals x over 2, or half x. And then we're going to square root both sides. Remember, when you introduce a square root, it's a plus or a minus. And so what we end up with here is the equation y is equal to plus or minus the root of x over 2. Okay, now that might look like something very foreign for you to draw, but we all know how to draw this parabola. It's going to look something like this. We can take the coordinates here at 0. When x is equal to 0, y is equal to 0. When x is equal to 1, then you've got 2 times 1 squared, and that's just 2. Same story here, minus 1 times minus 1 is 1, and then you square it. So there's the basic form, and then if you wanted to, you could then reflect those points, and that would help you to determine what the reflection of this in the line y equals x is going to look like. So if we reflect, then we are dealing with this. So there's our function f minus 1. There's our function f. Okay, what was the problem? The problem was that they wanted this to be restricted so that the inverse is a function. Okay, why is this inverse not a function? Because if I were to put my ruler here, it would cut in more than one place. Okay, so it's not passing that vertical line test, but that's okay. What I can do then for question 2 here is I can simply, so that was question 1, I can simply restrict my original function. So basically, if we were to pretend that we only had the top half of this graph, that would be a function. Because as you'd follow my ruler, you are ignoring that bottom half now. It's now invisible to you. You will see it just cuts once, okay? And in a similar way, if we were to pretend that we only had the bottom half of this function, so now we would ignore the top, we would once again be able to pass that vertical line test. Okay, but what they want us to do is restrict the original function. So basically what we'd need to do is we'd need to say, well, either we're going to take this part here, or we're going to take this part here, but we can't reflect both of them at the same time. Okay, so what would we say? We would have to say that either x is smaller than or equal to 0, or x is greater than or equal to 0. Okay, so basically all the x values on that side or all the x values on that side, but not both of them together. Let's take a look at this one. F of x is equal to minus x squared. We are going to start by saying, okay, in the place of y, I'm going to write x. In the place of x, I'm going to write y. And then I'm going to need to get rid of that negative. So let's divide by minus 1. What I do to the one side, I'll do to the other side. So we end up then with y squared equals minus x. And then we're going to take the square root of both sides, plus or minus there. And I'm immediately having alarm bells here. Okay, y is equal to plus or minus the negative x there inside my root. Okay, why am I worried? Because inside a square root, I cannot have a negative value. So straight away, I'm starting to think about some kind of restrictions here. X, how am I going to make this positive? Okay, it's a minus x. So basically, a minus times a minus will give me a plus, and I'm allowed to root a plus. Okay, so basically, x has got to be negative numbers here. Think about that carefully, okay? Why does x have to be negative numbers? Because a minus is already under the root sign, and a minus times a minus is a plus. Any positive number that I put in there will then multiply by that negative. We'd end up with problems. Let's look at the sketch here. So this is the graph of f, okay? This is from grade 10. We could already do this. It's negative, so the a value is negative, so we're looking at what is called a maximum value parabola, or what many math teachers would just say a sad face parabola. x squared. It hasn't really shifted anywhere away from the axis. So there is our basic graph. Okay, and now what would this reflection look like? Okay, well, let's start and just plot it, and then we'll see what's going to work for us. Here we have the sketch, and grade 12s, I think you'll be happy to note, have a look at what the domain is of this inverse. Do you note that it is only values on the negative side of the y-axis? So basically this criteria is automatically met. This whole graph here, this whole relation, is occurring where x is smaller than or equal to 0. Okay, but that doesn't answer our question there for question 2 when they've asked us to restrict the domain so that it is a function. So it is currently not passing the vertical line test. I am going to need to restrict the domain then and say, okay, well, either we can take the negative side, which will then map to that part over there, or we can take the positive x values of the original function, which will then map to that section there. So once again, our restrictions are going to look very similar. So x needs to be either smaller than or equal to 0, or x needs to be greater than or equal to 0.